Okay, so optimization problems. These are problems where what we're trying to do is we're trying to find the value of x that gives either the maximum value of the function or the minimum value of the function. So the idea is that we're trying to choose the value of x that will give us the most of a good thing, like re-election probability if we're a politician, or if it's a minimization problem, we're trying to get the smallest possible amount of a bad thing, like error in our estimates in statistics. And we got a hint of an optimization problem in the last workshop, workshop 5, where we just sort of observed that our measure of net benefits in the one problem increased for a while and then it decreased. For a while, its first derivative is positive, and then the first derivative became negative. And that's how you find you're at the maximum. Well, the first derivative is increasing. The fact that it's increasing says that you can get more of that function by increasing your x value. If you get to the point where it starts to decrease, what that's saying is, no, you've gone too far. You can get more of the x value by decreasing, or you get more of the functional value by decreasing a little bit. Okay, so that's what we're trying to do in general in optimization problems that occur throughout math. It's a huge part of applied math in particular. So just kind of getting some lingo and notation down, the way we would write that kind of problem is like this. We would say, choose x to maximize f of x. Okay, so x is, we call it the choice variable. It's an R there. And f of x is the objective function. If you're looking right now, you're thinking there's something going on in that objective function that looks a little bit weird. I'm going to fix it. There should not be a prime here. We'll get to prime soon enough. We are going to be taking derivatives, but what we're looking for here is the primitive function. Okay, so the thing that we care about is the objective function. And as I say, if it's a good thing, we're going to try to maximize it. If it's a bad thing, we're going to try to minimize it. The thing that we can control is the choice variable. So these optimization problems are very practical in the sense that they're telling us, okay, what do you can control x and you want the most f as possible. What do you do? What x do you pick? Here. All right. And so what we're looking for, sort of draw kind of an arbitrary f of x that has a maximum to it. We're looking for this kind of the top of the hill here. And what I was arguing is that here, before we hit the top, we're in this range where the first derivative is greater than 0. We'll keep going. You could tell this has got a negative second derivative, so that positive first derivative is getting smaller and smaller. And at one point here, it's flat, and then it starts to become negative. Okay, so over here, f prime is less than 0. It's right here at this sweet spot that I'm going to call x star. That is the point where the first derivative is exactly 0. Okay, and that is the point that could be a maximum point. Okay, so this is this condition that at the critical point, I'm going to put the star here. The first derivative has to equal 0. This is called the first order condition. Let's try to prove some writing here. First order condition. You might have learned to abbreviate it FOC. That's how I was taught to do it. And the first order condition is necessary. You're not at the top of the hill unless your first derivative is equal to 0. And again, it's that same kind of logic. You're not at your maximum point if your first derivative is positive, because what it's telling you, if you're at a point where your first derivative is positive, it's saying, keep going, increase x, you'll get more. And if your first derivative is negative, it's telling you, no, 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 back up, decrease x, and you'll get more. It's right at this one point where the derivative hits 0, and in this case, it's going from being positive, we're going up the hill, to being negative, we're going back down the hill. It's right at that point where the maximum occurs. Okay, so the first order condition that the first derivative equals 0 is necessary for a maximum, necessary for x star to be a maximum. Okay, so this is a pretty conventional way, and when we're solving optimization problems, to talk about our maximizing values, or ones that might be maximizing values, which is the status of what we've got right now, to denote them with a star. It's optimal, potentially optimal value. Again, the technical name for it is that it's a critical point. Okay, so let's just do an example. The function I drew here looks pretty close to this function. So choose x to maximize 2 minus x minus 1 squared. Okay, that's reasonably good drawing of what that function looks like. And so what we're looking for here is an actual number. We're looking for the number here, the x value that corresponds to the highest value of the function. And we're just going to go through the process. So the first thing I'm going to do is find first derivative of that objective function. So taking its derivative with respect to the choice variable, its derivative with respect to x, that 2, that's just a constant, it doesn't have a derivative, but it's the negative that's outside here. Then using the power rule, so negative 2 x minus 1 to the 2 minus 1, the first power, checking the derivative of the inside, there's just an x there, so no chain rule to worry about. This is my first derivative. Setting it equal to 0 makes it a first order condition. So find the first derivative. 2 is set it equal to 0. And then 3 is solve for the critical point. Okay, so solving for my critical point, negative 2 plus 2 equals 0. Negative 2 there, just multiplying out this tricky algebra here. And that gives me x equals 1. All right. So what the first order condition is telling me is I'm looking for that point where this function has first derivative of 0, and that happens at the point where x equals 1. Okay, so that x star is my critical point. It's my, if there's a maximum here, it's going to be at 1, because the first order condition is necessary. Okay. So it seems like we're done, right? But the problem is we're not quite done. And so to show you that we're not done, let's go to a new page here. And let's look at two functions. Our workhorse function here. This is f of x equal x squared. And this one is f of x equals negative x squared. Okay, and suppose I want to maximize that function. So I look at the first derivative and set it equal to 0. 2x equals 0. My critical point here is 0. Okay. For negative x squared, if I wanted to do the same thing, set its first derivative equals 0. Its first derivative is negative 2x. That also happens at x equals 0. Okay, so here's the thing. In terms of first derivatives, yes, the first derivative is 0. at the top of a mountain, but it's also 0 at the bottom of a canyon. And the last thing we want to do if we're trying to get the most of a good thing is accidentally pick the value that gives the least of it. And the problem is that the critical point could be maxima or they could be minima. The first order conditions are the same for maxima and minima. We can't tell from the first derivative if that critical point that we found corresponds to the bottom of the canyon or the top of a mountain. Okay, so the final step in sort of solving your basic, most simple optimization problem, after you've taken the first derivative, set it equal to 0, solve for the critical points, the final step is then to classify those critical points. So that's the last thing we're going to do here. Okay, so I'm going to talk about 3 ways to classify the critical point. These are not the only ways. Optimization theory is a really big subject. You could take a whole course in it, and there's lots and lots of ways of classifying critical points. But I'm going to go over the 3 that are simplest, you're most likely to run into, work in lots and lots of situations. Okay, so for all of these, we're just going to assume that we're talking about a critical point. We're talking about some point where some point x star where the first derivative equals 0. So one way we can tell whether we're at the top of a hill or the bottom of a canyon is we can just look to see if that first derivative that is equal to 0, is it in fact changing from being positive to negative? That's what happens at the top of a hill. Or is it changing from being negative to positive, is what happens at the bottom of a canyon? Okay, so if f prime of x is less than or equal to 0 for x less than x star, and first derivative greater than or equal to 0 when x is greater than or equal to x star. So if we're going from a negative first derivative to a positive first derivative, I know you see it, there's the bottom of a canyon, that tells us that x star is a min. Or if we're going to be really careful, we would say x star gives us a minimum value for the function. I'm just going to be a little bit loose and call it a minimum or a minimizer. So that's maybe part A of method 1. Part B then is the opposite. If that first derivative is greater than 0 for x less than x star, and it's less than 0 for x greater than x star. Okay, so it's greater than 0 as x is below x star, and then it becomes less than 0 when x gets bigger than x star. That's we're going from going up to going down. That's our top of a mountain, and x star is the maximum. Okay. This is kind of an underappreciated way to classify the critical points, because often when you found the critical point, you've just been looking at this equation that finds the points where x is exactly equal to 0. And sometimes you retrace your steps through the algebra, it's pretty clear what it was on either side of the cut point, so to speak, what values of x it was positive for or negative for. Okay, so one way to classify your critical points. Yeah. Another way, I have space for it here. So again, we're still assuming that we've got a critical point here. We've got a point where the first derivative is equal to 0. If the second derivative is greater than or equal to 0 for all x, okay, then we would say the function is globally concave. Then we would say the function is, I got it backwards. This is one of my favorite things to get backwards. You really have to watch me on this. When the second derivative is positive, it means the first derivative is increasing. It goes from, at a critical point, being negative to becoming positive and steeper. That corresponds to convex. I think I said concave before, but positive sign on the second derivative means a convex function, and if the function is globally convex, the critical point will be a minimum. The other case, if the second derivative is less than or equal to 0 for all x, this is the function that is globally concave. And that means that the x would be, that the critical point would be a maximum. Okay, so two ways here to classify critical points. One is just by looking at the sign of the first derivative on either side of the critical point and deciding just based on the first derivative by itself, whether you're going from negative to a positive first derivative, that would be a minimum, or from a positive to a negative first derivative, that's a maximum. Another way is to see if you have a function where the second derivative always has basically the same sign, okay, the same sign or 0. If it's always non-negative, always greater than or equal to 0, so the second derivative is always greater than or equal to 0, as a globally convex function, and if it has a critical point, that critical point can only be a minimum. If the function is globally concave, if the second derivative is always non-positive, okay, less than or equal to 0, then any critical point that function has is going to have to be a maximum. So two ways to classify the critical points. Third way is to actually look at the second derivative at the critical point itself. Okay, so we've got two processes for classifying critical points that kind of correspond to broad intervals, how the function behaves across its whole domain. And lots of functions are kind of simple, like they do have the same second derivative across the whole domain. If you have a function that's curvy and is going to have, those functions will have lots and lots of critical points. For those, we have to usually look at the second derivative at each critical point. Or it's another trick that is most helpful in that situation. Okay, so we're still reminding ourselves that we're at a critical point here, point where the first derivative is equal to 0 here. And our third way of classifying that critical point is to look at the second derivative evaluated at the critical point. Okay, so maybe the second derivative doesn't always have the same sign, but you put in the value for that critical point, and if it is strictly less than 0, then that critical point is a max, and if it is strictly greater than 0, it's a min. Okay, the problem with this, or the limitation, I should say, with this method is if the second derivative at that critical point equals 0, it's inconclusive. Okay. Second derivative equal to 0, you could have a minimum, you could have a maximum, or you could have neither one. Okay? So not every critical point even necessarily corresponds to a minimum or a maximum. Okay. So that's overall the basic process, and this, as I say, is enough for a lot of the optimization problems you guys are going to encounter as social scientists. I've got one more lesson actually 2 more lessons in this unit. The next one is going to give you a brief introduction to some of the trickier issues that arise in optimization. So I'm kind of trying to send a nuanced message here. On the one hand, this basic find the critical points and classify them, that is optimization in a nutshell. And if you know that, you really know a very large fraction of what there is to know about optimization. But then there's a whole lot of fiddly details there. Because optimization is such a big part of how we apply mathematics to science, to engineering problems, to statistics, to all of this, we have a lot of techniques that have been developed to address some kind of special issues. And I'm going to give you a very, very broad, very, very shallow, I guess I should say, introduction to some of those issues in the next lesson. So I'll see you then.